Review. This is Dr. Butler and this is AP Chemistry. We're going to review Unit 4, Chemical Reactions. So these are the points that we want to touch on. First of all, we want to know about the introduction, just a basic idea of reactions, what they are. Be able to do balance equations and, of course, net ionic equations. Being able to represent reactions. How do physical and chemical changes play a role, stoichiometry, and then the types of chemical reactions. So first thing there is the introduction to reactions. And basically this is the idea that a chemical reaction is a chemical change. Okay? Physical changes are not reactions, but there may be a significant change, but they are not reactions. So chemical changes are reactions, and we usually can identify those by, we identify those by seeing one of the changes in a reaction. For example, we would have a color change. Often would represent a chemical reaction. A precipitate can form. A gas can be evolved from the solution, or you could have a heat change, like it gets colder or it gets hotter. And the final one was sound and light, which is usually represented by fire or explosions. So those are chemical changes, and they usually indicate that this is a chemical reaction and can be represented by a chemical change. So that's just the basics of it, but the meat of the chemical reactions is the chemical equation. And so being able to write out chemical equations, balance chemical equations symbolically with the symbols, showing the conservation of the mass. And the conservation of mass principle is just that the number of atoms that you have remains the same. The number of atoms does not change. So the bonds may change, the formations may change, the chemical compounds may change, but the number of atoms stays the same. And I think that we are pretty good with the balancing, just generally balancing. When you get an overall equation, that is a molecular equation. If there's ions in it and you break up the ions in aqueous solutions, then you get the complete ionic. And then if you cancel out the spectator ions, then you get the net ionic equation. So you should be able to change a molecular balanced chemical equation into a net ionic equation. And I'm just going to do a real quick example of this and see how you guys can do. Let's say that I have some sodium hydroxide, which is an aqueous solution. And I react that with a calcium chloride. Okay, I apologize for not having the subscripts, which is also in an aqueous solution. And then that reacts to form salt, which is aqueous, and calcium hydroxide. Okay, which is a solid. And so we get this solid formed out of there. So first of all, you'd have to balance the equations, making sure that, let me give me some space for coefficients, making sure that you're, making sure that the number of atoms is the same. I can do this pretty quickly with an equation like this, and hopefully you can too. I notice that there are two Cl's on this side, and so I can put a 2 in front of the NaCl, but that ruins my NAs. So I could put a 2 in front of my NaOH. That gives me 2 hydroxides, which I have 2 hydroxides over on that side. So that's a balanced equation. If you remember then, going from a molecular to a complete ionic equation, I have to break up the ions. So let me do that with a typewriter. Anything that's aqueous, that's an ionic compound, breaks up. You keep the coefficient. So we have our sodium plus breaks up with our hydroxide minus. I'm going to not put the word aqueous in there. My calcium, which is 2 plus, breaks up with my chlorine, and there are 2 chlorines in there, 2Cl. And then that turns into my other side, which is 2Na plus 2Cl minus plus Ca2 plus 2OH minuses. All right. Oh, actually, hopefully you recognize that. We do not break up solids. Only aqueous do we break up. And so these are our net ion. That's our total complete ionic equation. Now we look for things that are spectator ions. Well, the sodium is spectator. It does nothing. The chlorine is a spectator, and so then that goes over there. And then you just rewrite the final bit, and I'll try to rewrite it like this so we can see what the minus sign goes up there. OH is aqueous, and then we have the Ca2 plus, Ca2 plus, that is also aqueous. And these things react with each other, sorry about the messiness, to form our CaOH2. And that is a solid. Okay, so this is our net ionic equation that we would use to represent. The very important, let me star that. That's something that we really need to know how to do. All right, representation of chemical reactions is just the idea of being able to represent them symbolically. This is our chemical equation, and to be able to represent them with drawings. You also need to know all the symbols that you can use. States of matter, so we should know what the states of matter are. S is a solid, L is a liquid, G is gas, and of course the aqueous one. To show a precipitate, you guys should know how to do that. A precipitate is a down arrow. Next to that, in a gas evolved is an up arrow. To do that, you could also see the triangle, which represents energy or heat in an equation. All right. Physical and chemical changes in general. We mentioned this already at the beginning, but breaking bonds, forming new bonds is a chemical change in a chemical reaction. So changing the connections is the physical change. Changing IMF interactions is not. So that is not a chemical change. It's not a chemical reaction. There are some gray areas like dissolving. So if I took sodium chloride and I put it into water, then I could represent this by saying Na plus Cl minus. Now, is this a chemical reaction? No. It's a physical change, but it kind of is breaking up an ionic bond. So it is a gray area that you have. So recognizing some of those things. All right, stoichiometry, mole island. I'm not going to go over this. I think you guys can do that, but this is something that you do need to be able to do. Calculate the amounts of reactants. Calculate the amounts of products relative to each other. If you're given the grams of a reactant and you need to know how much is going to be produced, use mole island to do that. The mole ratios are represented by the balanced chemical equation, so you need a balanced chemical equation. So balanced chemical equation is necessary. A mole island, or at least the principle of it, you don't have to have mole island, but just the principle of it, using that's dimensional analysis, being able to represent that. You need a periodic table to do your molar mass and different things like that. You may even need to use the ideal gas law to be able to figure out moles of a gas or something like that. So you need to be able to do that. The important things is if you may have to calculate moles, You may have to calculate grams, that you would need molar mass. You may have to calculate number of particles. You'd need to know 6.022 times 10 to the 23rd. You may have to calculate liters. You would need to either use ideal gas law, or if it's at STP, standard temperature and pressure, you could use the 22.4. Heat depends on the enthalpy of the reaction. And so you can do stoichiometry with all of those things. All right, and connected to stoichiometry, we did this in the last unit with acids and bases, is titrations. So a titration is a method of determining the moles of one substance when you know the moles of another. And so you have some unknown molarity. And this is basically stoichiometry, except for you're doing it with using mixing chemicals. So the equivalence point happens when you may have substance A and substance B that you're titrating together. There's some indication that if A was an acid and B was a base, and we put an indicator in there, then we would know when the end point happened or the equivalence point happened. At the equivalence point, then our moles of A is going to equal the moles of B. Okay, according to the chemical equation. If there's a coefficient of 2 in front of A and 1 in front of B, then you need double the moles of A to balance the B. But most of the time it's going to be a 1-to-1 ratio. So the moles equals the moles, and you can calculate things based on that. And so this is where you're really titrating and doing that. We just did an example of that in the lab. So titrations are something that you could be tested on and understood. Acids and bases in general are just very general form introduction of acids and bases. You are not going to have to get into the details of them, but titration is one of those things that you should do. This last point here is be able to recognize endpoints like color change. You would use an indicator if you were going to be doing color change, or pH changes. You could find a pH curve, and when it shoots up, then you know that you reached the equivalence point. So titrations. And then the final thing is different types of chemical reactions. We'll go over a couple of these in a couple slides because there's a lot here. So these are the main types of chemical reactions that you could do. Here, I'm gonna do a little. Okay, so you got, we have acid-base reactions that we do. Acid-base reactions involve NH+. Redox reactions, that's been a long time ago when you do that. They involve transferring electrons and changing the oxidation state. Combustion is a specific kind of redox reaction. It involves a fuel and oxygen. If the fuel is a hydrocarbon, then the results are going to be H2O and CO2. In redox reactions, you need to know what gets oxidized and know what gets reduced. So oxidation and reduction. Oxidation means that you have gained charge by losing an electron. Reduction means that you've lost charge by gaining an electron. So oxidation and reduction processes, you need to understand those. And then oxidation numbers. I would like to spend some class time doing redox reactions because I think it's been a while since we've done that. And so we could look at that. All right, so the next kind of reaction is a precipitate reaction. This is when it's usually a double replacement. You mix two substances that are soluble, two ionic compounds that are soluble, and they form an insoluble compound. You would have to use a solubility rules chart to be able to figure out which one is insoluble. There's hopefully you are starting to recognize some of those things. We also talked about synthesis, decomposition, single replacement, double replacement. In general, those are not terms you need to know, but they're good, helpful hints to be able to predict the products. And so you would need to do the terms you should know is acid base, redox, or oxidation reduction, precipitate reactions. Those are ones that you should know for sure, and combustion. So specifics about acid and base that you should know. You should be able to distinguish between Arrhenius and Bronsted-Lowry. Acids and bases, Bronsted-Lowry is the one that's most important. Bronsted-Lowry is a transfer of a proton. Remember that a proton is a hydrogen ion. So one thing is going to lose the proton, that's your acid. One thing is going to gain the proton, that's your base. So reactions take place in water, and that's very important because water is going to lose has already OHs and H pluses in it, and so you need to be able to recognize those. And then the conjugate acid-base pairs, being able to identify those and do those. So we just did that in the last chapter, and we were nearly done. All right, so acids and bases. I'm not going to focus on this because I think that we are pretty good on that. We just did that, but review it if you feel like you need to. And finally, redox reactions. One thing that I have not covered, and I did not think that this was going to be on there, is balancing redox reactions using half reactions. All right, so this is a different sort of thing. In a redox reaction, you have two kinds of reactions that take place. You have your reduction reaction, and you have your oxidation reaction, and they both happen at the same time, and you need to balance the reduction reaction and balance oxidation reaction separately. I am going to do a video I'm going to find a video just about this redox reactions because I think it is important. I thought it was something that was not going to be tested because I thought it was in units 8 and 9, but apparently it's in unit 4. So that's the one. I think that's the only thing I missed in this, but hopefully you'll be able to do that. Okay, that is an overview of Unit 4, and hopefully that helps to do that.